So for introduction, I hope you attended on Monday the PGA and imaging theoretical session, and we discussed already about the basics of this technique. So if you consider the portfolio of neutron technique, there is diffraction and scattering for nanoscale and microscale structure. There is neutron imaging for macrostructure, which means kind of tenths of a millimeter or above. And we have elemental composition measurement techniques where we, let's say, count the number of atoms or nuclei in our sample in order to gain information about the chemical composition. There are two ways of determining elemental composition. One is called probe gamma activation analysis, and there is another one which is called instrumental neutron activation analysis. The common in these two techniques that they are so-called panoramic analysis techniques, so you can analyze almost every element at once. It's non-destructive, at least it doesn't need any physical sampling. It's metrologically accurate and very precise, and it's a bulk analytical method. That means both neutrons and gamma rays penetrate deep into the material and can deliver knowledge about the representative composition of the sample. Most other analytical methods like X-ray fluorescence or pixel are surface analytical techniques, so they can penetrate to the material only to a few microns or tens of microns. And instead of non-homogeneous or layered samples, this sampling volume is not representative to the composition of the entire sample. And in this case, nuclear techniques have advantages. So PGAA belongs to the family of nuclear analytical techniques, which is a branch of analytical science where natural or induced radioactivity or nuclear reactions are used to obtain information about the composition of the sample. And the neutrons interact with the atomic nuclei and not with the atom and not with the electron shell. So these methods, and the analytical signals of these methods are completely independent of the chemical environment of the atoms. So we just count the atomic nuclei and we don't care about the chemical bonds. That's why it is applicable to element analysis. Interestingly, neutron activation analysis was invented by a fellow Hungarian, György Hevesi, in 1936, who later became a Nobel laureate. And PGA was also observed very long time ago, already in 1934, when a block of paraffin was bombarded with neutrons and some radiation with high penetration power was observed. And later it was identified as the gamma radiation of the hydrogen, the neutron capture. As this is a nuclear analytical technique, we use on the daily basis this chart of nuclides, which is the periodic table of nuclear physicists, let's say. So in this map, we plot in 2D the number of neutrons or number of protons, and we can also demonstrate different nuclear reactions on this chess table plot and see a certain isotope, how could it be produced. There is a convention for the notation of nuclear reactions, which is like this. So first we put the target nucleus, then in parentheses we put the the incoming and outgoing particle, and at the end we put the target nucleus, the product nucleus. And if you express this, like a chemical reaction, you can decipher this very short notation. And of course, the energetics also plays here a role. So as just like in chemistry, where you can have endotherm or exotherm processes, here we also have energetically favorable or not favorable nuclear reactions. And in this case, it's called threshold reaction, where the projectile particle has to carry in some kind of kinetic energy to the system in order to realize the reactions. As we discussed already Monday, neutrons are neutral particles, and in free state they are unstable. So they decay with a half-life of kind of 10 seconds to a proton, an electron, and an antineutrino. So that's why you have to always freshly produce neutrons, and you cannot store them for later use. And energies of neutrons can span over a very wide energy range, from milli-electron volt up to mega-electron volt. And different energy neutrons can create different nuclear reactions. Our main focus is on the so-called N-gamma reaction, which is the practical basis of the prom-gamma activation analysis. So here we bombard our sample with neutrons, and this neutron is captured into the atomic nucleus. And this neutron has a binding energy, so it will attract other protons and neutrons in the atomic nucleus, which were already there. And this binding energy is in the order of 7 to 9 mega electron volt in most of the cases. And this is such a high value that the kinetic energy of the neutron is often negligible. And once the neutron is embedded into the atomic nucleus, we create a so-called compound nucleus, which has an excess energy. And it emits this excess energy in form of gamma radiation, or probably with charged particle emission. But we have nuclear levels, just like electron shells, and in between these nuclear levels, transitions are possible. So you can have a direct transition down to the ground state, or you can have a series of gamma emission, which is called a decay chain or emission chain. And there are rules, nuclear physics rules, to say which transition is more probable on a load or not. And then we get this product nucleus. This product nucleus can be either stable or can be radioactive. So a further step can happen when radioactive decay happens. And in this case, another kind of gamma emission is possible, but this doesn't come immediately after the neutron capture, like from gamma activation or from gamma radiation, but this is governed by the half-life of the radioactive decay. And this is the basis of the so-called instrumental neutron activation analysis technique, while these from gamma radiations are used in PGAA. In low neutron kinetic energies, we have a rule which is called 1/v law. That means the slower is the neutron, the lower is the kinetic energy, the higher is the neutron capture cross-section, so the probability of capture reaction. This can be explained very simply because if the neutron flies at a lower speed, it will spend more time near the atomic nucleus. So there is more time for the interaction. And that's the reason why we prefer to have low energy neutrons, because with the equal number of neutrons and equal number of atomic nuclei in your sample, higher reaction rate can be achieved. So analytically speaking, higher sensitivities can be achieved using slow neutrons. The neutrons are produced in our case in the so-called Budapest research reactor, which is a 10 megawatt tank type research reactor. It's water cooled and water moderated. So it's like an energetic reactor. It has all the features of it, but it's much smaller in thermal power, of course. But in contrary, the thermal flux in the active zone is much higher than in an energy production reactor. So this could be used for scientific research and material aging studies as well. The slow neutrons are delivered from the production site, so from the core of the reactor to the experimental stations by so-called neutron guides. Neutron guides are light optical devices, and they take advantage of the wavelength nature of the neutrons. If a wave approaches an interface of air and the condensed matter at a low angle, it is reflected rather than absorbed. And with a series of reflections, we can deliver the neutrons far away from their production site, but at the same time, we can reduce the unwanted high energy components of the neutron beam, and we can also get rid of the gamma radiation. So this is a very essential part of the measurement system. And as I mentioned, there are two ways to do element analysis. This is the one way when we deliver the neutrons to the sample into an external beamline. The other way is the instrumental neutron activation analysis, where we put the sample into the reactor core. We let it irradiate it for some hours, and then afterwards we remove it, and in a separate step in a counting laboratory, we record the decay gamma radiation. And so these are two independent ways to do element analysis by neutrons, and they are more or less complementary to each other. So Na needs much lower sample mass and relatively easy sample preparation, because we need to put the powder sample typically into a glass vial, and this goes to the reactor for irradiation. In case of PGAA, you need higher sample mass. The sample preparation here is also very easy. And the difference is that for Na, we separate in time and space the irradiation and the counting, while for PGAA, these two things are happening at the same time. The disadvantage of neutron activation analysis is that you have to measure the artificially induced radioactivity in the sample several times. So the entire procedure can take weeks even. But in exchange, we have very low detection limits and very high metrological quality. The PGA gives you instant result, so the spectrum is collected on the fly, and we can deliver almost immediately within a few hours the composition. But the downside of PGA is that its detection limits are not so low as neutron activation analysis in reactor. Here we typically measure the major components and the minor components, and in addition we can measure a few trace elements where for nuclear physics reasons the sensitivity is very high, as indicated here in red. But in most cases the sensitivity or the detection limit of the method is around 10 ppm or 100 ppm for most of the elements. The spectrum is quite complicated for PGA. We have several hundreds of peaks. This is on one side makes the evaluation labor intensive, but on the other side it gives you inherent redundancy. So one element has more than one line, and if you evaluate all of them and cross-check them against each other, then bad fits or interferences can be ruled out very quickly, and that makes possible to have a very satisfactory and reliable result. In a polychromatic beamline, just like our guided beam of neutrons, the reaction rate, which is denoted by R, comes as the integral of the number of atoms in our sample, the sigma, which is the differential cross-section, so the neutron capture cross-section as a function of neutron energy, and the phi, which is the flux, so the number of impinging neutrons per square centimeter per second and per electron volt. And this should be integrated over the entire energy range. But in practice, this is too complicated. So we created an artificial quantity called the thermal equivalent neutron flux, which is a hypothetical number of neutrons with a given velocity, 2,200 meters per second, that would give you the same reaction rate as this complicated equation. And as long as the 1/v law is valid, then we can use this simplified formula, which is much more practical. So our goal is to know the mass of the element in our sample. And in order to achieve this, we record the spectrum where we have peak areas. And these peak areas are proportional to the masses and the measurement time via this S sensitivity factor. And this is, can be expressed as the multiplication of several natural constants like Avogadro number, molar number, the isotopic abundance of the selected isotopes, the neutron capture cross-section, which is available from tables, and there is this P gamma, which is the number of gamma rays emitted for one neutron capture. So this is a number between 0 and 1. But in practice, these three things should be determined as one compound nuclear quantity, which is called sigma gamma, and this is called the partial gamma ray production cross-section. And this we have already tabulated in the spectroscopic libraries. We have the flux, which is the number of neutrons, and we need to know also the detector efficiency from calibration as a function of gamma energy over the entire energy range. We also need to consider the dynamic range, which is in correspondence with the detection limit. So if we can detect one material in another, then we can do the other way around, and this makes the dynamic range. So mass spectrometric methods are known to be the broadest dynamic range, but this gamma spectroscopic method has something like 10 to the 6, 10 to the 8, but usually it is not symmetric. So that means we can measure, say, 1 milligram of hydrogen in 1 gram of chlorine, and we can do the reverse thing. But if you count it in units of atoms, it's not completely equal. Okay, so the general features of PGA, which we have to know, is that it delivers the bulk composition of any solid or liquid sample, so it's very representative, and it's not very much influenced by surface effects like patina or corrosion or paint or protective layer, because the sampling is more representative to the bulk of the sample. The minimum sample mass is kind of 100 milligram, but to some extent we are flexible because we can compensate the smaller amount of samples by increasing the acquisition time. It is panoramic analysis technique, so in principle all chemical elements can be measured except for the helium, which has no capture line. And as I told, the detection limits are medium range, so not the most sensitive method, but still sufficient for many applications. PGAA is completely non-destructive. That means the sample can be returned to the user without any harm or without any destructive sampling or dissolution or fusion. So it's very well applicable to objects where the object is either not possible to dissolve completely, like geological materials, or it's too valuable for dissolution, like material science samples or heritage science objects. And with this technique, we can determine the composition and return the object intact to the owner. We also don't need to do any significant sample preparation. If the sample is self-supporting, then it can be placed into the sample chamber without any preparation at all. We have a scanning sample stage, so smaller parts of larger objects can be also studied, and the local composition can be determined. And the beam size can be changed from 5 square millimeter up to 2 by 2 square centimeter. So this can be adjusted based on the question we need to answer. So this summarizes what I just told. So when do you need to consider PGAA experiment? When your sample is either expensive or valuable, like a heritage science object, where you need in-depth composition instead of surface composition, which other methods cannot deliver for you, or the sample is very difficult to dissolve, or you are worried about some digestion losses or additional impurities that you carry in during the sample preparation, or when your sample is not stable in time, because this method you can use for in situ monitoring of dynamic processes, or in situ measurements of equipment which can be installed in the beam line. So here you see some photographs of the facility. This is the sample chamber. This is the cabin. Here we have next to the cabin, we have a low-level counting chamber for checking the radioactivity of samples. And this is the data acquisition part of the facility. And this is the dip station. So from here, I would like to present you a series of videos where we illustrate the key steps of the measurement. If you have a powder sample like this, it can be geological sample or material science sample. We just simply wrap it into Teflon foils. Teflon is advantageous because it consists of carbon and fluorine, two elements which have a weak analytical signal, and those lines are very well known, and that's why we can correct for that, the influence of the packaging. So I will start the video. I hope it will show up. Can you see this? No. Oh, bloody hell. Come on. Can you see now?
Yes, no.
Oh, very good.
Yes.
So typical sample types. This is the breakdown of the usage of our facility. So there is a section for nuclear data measurement and nuclear physics. There is a significant proportion dedicated for heritage science applications, so archaeometry. There is a section for material science, and the rest of the beam time is allocated for training and method development. So here you see some samples which we typically analyze. So these are geological samples like gemstones or chipped stone fragments, or some sea animals, ceramics, whole rock samples. So it can be like this big, which is 5 kilos, or we can measure alloys like coins, where you have a cladding layer. So with X-ray fluorescence spectroscopy, you would get a biased result. And now I would like to demonstrate the procedure how we seal the sample into Teflon foil. We have a 25 micrometer thick Teflon foil, and out of this we create a little bag, which is kind of 2 centimeter by 3 centimeter large, and there is a heat sealer, this blue device over here, which we will use for sealing the bag. So as I mentioned during the lecture, the sample can be slightly radioactive for a short period of time, so for a few hours, let's say. That's why it is very important to keep the powder in a closed form to avoid the contamination of radioactivity in the facility. And so here is a little solid sample that we can put into this Teflon bag. And we usually measure the weight, but seriously speaking, this is not required for the calculation. Because in some cases we do not irradiate the entire sample, so that then this balance weight is not relevant to the measured masses. In the second example, we pack a powder sample, which goes almost the same way. You have this prepared Teflon bag. You put into the powder, which is a kind of 1 gram, and then we heat seal the top part. And then again we make the weighting. And then we create such a little paper envelopes which contain most of the relevant information about the sample, like the sample code, the mass, the analyst name, and the date of packaging, and the mass of the Teflon foil. And then that's all about sample preparation actually. And this is done in our lab. And then afterwards we have to go to the neutron guide hole of the BNC in order to carry out the experiment. So this is the overview of the neutron center. So here is the research reactor, and here you see the beam lines for certain facilities. And PGAA is here. It's about 33 meters far away from the reactor core. And in these orange tunnels, we have the neutron guides, and they reach the facility right here. And then we will enter from here and arrive at the facility. So this is a radiation controlled area. So this radiation symbol is on the door. And once you enter, you see these orange tunnels for the neutron guides. This is the PGAA cabin. This is the sense machine, which you will probably learn a little bit later. This is the beam status indicator. And we have data acquisition hatches for many other instruments. And this is the layout of our cabin. So this is the entrance door. Here is the data acquisition for PGAA station. Here is for the NIP station. As you see here, we have two stations. This is PGAA, which is dedicated for the powder and liquids and relatively small samples, which are homogeneous. And the second station is called NIPS Norma, which is dedicated for the measurement of more bulky samples, like stones or heritage objects. Or here we can have a local composition analysis, and it is also combined with cold neutron imaging. This is a side view. The neutrons are coming from this direction. From here. And the neutrons are split into two halves. So the upper half goes to the PGAA station, and the lower half goes to the normal station. So these two facilities can be operated simultaneously and independently of each other, thanks to these apertures. And of course, we have beam stops where unused neutrons are absorbed. As this is a radiation area, we should also keep in mind the rules for health physics and protection of workers. So we use a lot of concrete and a lot of lead for shielding against gamma radiation. And we use adequate materials like aluminum, which have very low activation in order to minimize the gamma radiation doses. So you should know that if you plan a neutron experiment, then you should be very careful with the material choices. So if you place an equipment into the beamline, this should be made of materials which do not get activated seriously, and afterwards you can recover. So the most preferred material is aluminum or Teflon. For instance, iron alloys with cobalt content should be carefully avoided. And then we have the beam stops, and they are quite complex structures. So layer by layer, they absorb different radiations, and from outside, it's covered with blocks of lead. Here you see some neutron shielding elements. Also, these yellow plastic. It's a polymer loaded with lithium-6, and it has the feature that it can absorb the neutrons without generating secondary gamma radiation. So therefore, it is very applicable to the areas near the gamma spectrometer. But it's very expensive, so wherever it's possible, we use instead boron-loaded polymers like silicon, boron-loaded silicon, or boron-loaded paraffin. And these are also useful in combination with concrete. The removal of neutron and gamma radiation. Of course, we need beam status indicators to display the status of the beam. Green is typically safe and red is dangerous. So this is an easy explanation. Whenever you see red, you shouldn't go into this area. And the area is closed with a chain barrier. And just to highlight the operation of the deep station, here is this sample stage which can translate in X, Y, and Z, and also it can rotate. And this can be used to manipulate the sample. Here is the gamma detector assembly, and this is the neutron imaging camera. And this is the only facility where we can take advantage of the synergies of the two detector techniques. So we can combine imaging and local element analysis to support the exploration of the data. So here is for instance, here is a corroded iron nail, which was recovered from the bottom of the sea. And we measured locally the chlorine content. And it was possible to deduce that the corrosion was driven by the chlorine content of the sea, where it was buried. And the chlorine content is kind of proportional to the thickness of the corrosion layer. So this is how it works. So you can slide the side of the sample chamber to have better access to the sample. Down here you can see the sample manipulator. And here you see also sample frames, which can be used for manual sample loading. And this is a sample changer ladder, which can be loaded on the top of the motor sample stage. And this way we can program 8 data acquisition points. And with the script we can execute it without personal presence. And we have also a laser marker that can indicate the adequate position of the sample. So you can align your complicated geometry objects relatively easily to the measurement position. We can also create custom sample holders by 3D printing. So if you have an object which cannot stand, we can use such a custom coupling between the sample and the sample stage. This way we can safely measure the sample without the risk of breaking it. And of course, within the one object, we can also move and select measurement positions. For PGA, we have also a sample changer, which is here for 16 samples. So the samples for measurement are loaded here, and this arm is picking up one by one, loading it into the sample chamber, open the beam, measure the spectrum, and then return it to the storage position. And this goes on until all samples are measured. The detector, as I told you on Monday, it's a complex assembly of a high-purity germanium semiconductor detector. and scintillator detectors all around, surrounded by 10 centimeter of lead shielding. And this implements the so-called Compton suppression, which is an active baseline reduction technique in order to improve the detection limits. So here you see some samples already packed. So this is a white powder, it's not very well seen. And this is a gemstone. And so these are sample holders for the automated sample changer, and these are for manual sample loading. And then whenever the beam is off, you can walk to the sample chamber and load the sample. Like this. This is the counting electronics. It's a combination of several high voltage modules, detectors, spectrometers, and logical modules. Then you set the measurement time, or we also set a limit to the number of counts in the spectrum, and whichever happens earlier, we'll stop the acquisition. And then we open the beam, so you see that the indicator will turn into red. And then we start the collection of gamma spectrum. The typical measurement takes about 1-2 hours, and the energy range spans from 50 kilo electron volt up to 11 mega electron volt, so this is a rather broad range. And the spectrum is shown here with a logarithmic display. So this is a nice feature to enhance the tiny details of the spectrum. So here you see that peaks are already growing, and you can set up a so-called region of interest, where the program is counting on the fly the peak areas and the related uncertainties. Then once you are happy with the spectrum, then you stop the beam and you save the spectrum. Once the measurement is over, you can remove the sample from the sample chamber, and we have the devices to check the residual radioactivity of the sample. And immediately after removal from the neutron beam, this can be significant. So we store the samples for some hours in a safe place. And if we measure the radioactivity after a few hours of storage, then you see that it's very, very close to the natural background already. So the same sample can be removed from the facility and can be returned to the user without any further consequences. So once we have the spectrum, we have to evaluate the concentrations. And before going that, I show you two utilities which are handy. These are our own software. So this gamma viewer is just for checking the spectrum, viewing it. And you can see this very strange structure right here in the middle of the screen. And you can wonder why this is with such shape. So this is an exception. Usually the peaks are kind of Gaussian, but this was influenced by the Doppler broadening. As the peak comes from a and alpha gamma reaction. So the atomic nucleus is repelled, and the alpha particle and the atomic nucleus flies while the gamma ray is being emitted. And then this Doppler broadening happens, and it makes this boron peak quite wide, about 15 kilo electron volt wide. So this peak shape needs special treatment. And the other thing which is special is this one, which is called the annihilation peak. It happens at 511 kilo electron volt, and it is also broader than any other peak near there because of the pair production. So these two regions are handled specially during the peak evaluation. So this is a quick and easy way to estimate the peak area. We just simply integrate everything which is above the baseline and get a count. And not only the count, but also the corresponding statistical uncertainties are calculated, which is very important. We have a nuclear library, so we can identify the origin of each gamma radiation from this library. So this peak comes from iron. And here you see the library entries for the energies. And then for the real evaluation of the spectrum, we have another program called HyperMet PC that I will demonstrate you. Let me see this. Okay. So this HyperMet PC is the workhorse software for gamma spectroscopy in our lab. It was written by our former colleagues, and it's a very accurate and very sophisticated peak fitting software, but unfortunately technically quite old-fashioned. So the first step is that we load the spectrum. And then we can also have a magnification window. So if you drag this rubber band, then you can see the region magnified. Here you have all the data acquisition parameters like measurement time and the rough energy calibration. And then the first step is that I go to the evaluation, and then I create a file which will store the fitting data. I load the energy calibration. I load the nonlinearity correction. So nonlinearity, as I mentioned, is a small correction to the linear Chadwell number energy correspondence, which is characteristic to the data acquisition system, and it's rather constant in time, so it can be corrected for. And this allows the energy determination of gamma radiation down to 5 significant digits. So we can measure mega electron volts with tenths of, so one tenth of kilo electron volt precision. And this is rather demanding, but needs for accurate element identification. And then the next step is I can optionally load efficiency, but my personal preference is that I like to have it switched off. We can load it anytime, and then the results will be recomputed. And the first step is that we create a so-called automatic fit. So we let the program to go through the entire spectrum and start to cut it into smaller sections called regions. And each region is fitted with an adequate mathematical function, model function, which contains peaks and as well as background parameters. And the program will first try to do its best, and then afterwards we have to improve it. So this automatic fitting stage takes about 1-2 minutes, depending on the complexity of the spectrum. And then it's done. Coming to this results, I can enable the so-called residual window. So this is the residuum is the difference between the measured count in a channel and the fitted value of the model function. This blue region is the plus minus 1 sigma range, while this brownish thing is the plus minus 3 sigma range. So if the residuals are distributed according to the Gaussian distribution, then 66% of the channel differences should lie within this blue region, and 1/3 is roughly distributed between the blue and the brown areas. So if you have good eyes, after some time you will be able to assess the quality of the fit only on the basis of the residuals. And the more important information is shown here. So this is the peak position, which can be displayed also with more significant digits. So this symbol is for the plus minus sign. And then here we have the peak area in unit of counts and the corresponding uncertainty. And the merit of the fit is this so-called chi-square number. So if we do nonlinear least square fitting, then it can be proven that this chi-square has a expectation value of 1, and you can also calculate its uncertainty. So the program displays you this quantity, which is a transformation of this chi-square. And if it is shown in green, that means that you did a good job, or the program did a good job, and this region is from mathematical point of view, it's well fitted. From spectroscopic point of view, it can be still improved if you are the spectroscopist, but mathematically speaking, it's fine. And wherever there is a problem, this value will be shown in red, and that means you have to improve the fit of that region. Between the regions, you can jump between the plus and minus buttons. So my habit is that I start reviewing the channels from the top part of the spectrum down to the low energies, because the top part is easy and regular, so you can pretend that you are proceeding very fast. So here you see already some points outside of the blue region in the between the brown and the blue, but this is the normal, and it should be like this if the counts follow the Gaussian distribution. And then this fitting is very nice if you need to decompose overlapping peaks, because for well separated peaks, we could also do simple integration, and that would give you the same peak area. But whenever there is a peak overlap, then mathematical decomposition by nonlinear peak fitting becomes necessary. So this is the iron doublet, which I showed you in the previous video. And as you see, it has 1.5% statistical precision. Another one is 1.6. So if you start weighted averaging several lines of an element like iron, then you can end up in very good counting statistics. And then you go one by one, checking regions. So here you see already some overlap, which is nicely decomposed by the peak fitting. So if there is any problematic region, then the program is marking with this star symbol. So you can quickly jump and see what's wrong with this. And here you see that this chi-square value is shown in red because it's statistically higher than what one would expect. And in this case, the analyst should improve the fit. Improving can be done by adding peaks or removing peaks or splitting the region into two halves, which is usually helpful. So then I split and fit separately the first half, and in the same way I do the second half. And now I can remove this original region. And now the both regions are satisfactory in fitting quality. Do you have any questions or comments to this section of the presentation? Okay, so we can proceed if there is nobody who wants to have questions or answers. So we proceed like this. Here you see that there was something strange. So this is once again something that we have to correct. Now we reach this region where the annihilation peak is there at 511 keV, and this program can fit it only with several regular peaks. So this is not the most adequate way to handle it, but in practice it can also work. The goal is that all other peaks should be of right peak area, and the area of this peak is not used for any purposes, so we can fit it however it is possible in order to reach the chi-square values. And this is the boron peak, which is beyond the possibilities of this program. So I will demonstrate you that we will handle it later with another software package. So let's say you finalized the fitting, and all regions are properly handled. Then we refine the energy calibration. So we come to the calibration and we choose two peaks which are relatively large and good precision in also in our present spectrum, so from the point of view of fitting, and also it has good precision in our analytical library. So we know it's the gamma energy with high confidence. So here is, for instance, this 12,073. So if I click here, then the program will read the position of the peak wherever my cursor is placed. So if I place here my cursor, then it will read another value here, which is of course biased, but this is the peak what we actually need. This is the other one. Okay, and now we can also read in the peak width parameter, because the peaks are getting broader and broader towards higher energies, and this can be also calibrated with a square root based formula, and we can also read from the fit the width of the peaks as a function of energy. And once this is all done, then we can create a so-called report file. It's a peak list, and then we place it over here. So this is a file where we have a header like acquisition date, lifetime. So there is a difference between true time, which is the length of the experiment, and there is lifetime, where your counting system was able to count events. This is always slightly smaller than the true time, because in a little fraction of the time, the counting system is busy with processing one event, and it cannot accept another one while it is processing the previous one. So these two times are separately counted and registered. And then we have this table where we have the positions of all peaks in units of channels and also in energies. And here are the peak areas and the corresponding statistical uncertainties. But as you see, we fitted almost 600 of such peaks in our spectrum. Okay, and then we have another utility called gamma fit that can handle those regions which are not adequately handled by HyperMath PC. So we can exit from here, and then here is this other utility. We can open the same spectrum again. And then, so this is typically an addition to the HyperMath, and we will handle only those regions which are problematic in the HyperMath PC, sorry. So this was from one side, this boron peak, because this program has a built-in model for handling this boron peak shape. And if you see it from close, you can recognize that here is an additional bump, so here is another peak that we can add. Then the program will start the fitting. This takes a little bit longer because this involves a Fourier transformation and convolution step. But still, you see that the boron peak shape is quite well reproduced. We can further fine-tune the results. We can set different parameters of the model function. We can enable or disable certain background or peak components. And then, of course, we can repeat the fit. And then we have the peak area of boron right here, separated from this tiny area which corresponds to sodium, which is shown here. And this is a logarithmic view, so if it's switched to linear view, then this is even more remarkable. The other feature which we usually fit with this program is this annihilation peak. Here we have also a proper model. And here you can add one by one. Until nice fitting results are achieved. And you may notice that this peak is now broader than the others. So this is the annihilation peak, which is specially handled, while all other peaks are of common peak width. And then again, you have here all the peak areas listed with the corresponding uncertainties. And we can create a so-called PKF file from this utility, which is a kind of a table again, and it contains the same set of information as the PKL file. And once all these things are done, then we can proceed to the concentration calculation stage, where we have an Excel utility called Prospero. And the task of this program is to load the PKL file, so the peak list, and using the library, it will assign elements to each analytical line based on the energy differences. So the best match will be selected, And then afterwards, the mass of the element will be computed from all assigned analytical lines. And then the program will make a statistical check and rule out the outliers wherever there is an interference or some poor peak fitting. And the rest will be averaged. So each element which we detect in the sample will have one mass. And then at the final stage, we will consider the concentration of the elements as the ratio of the elemental mass what we detect over the masses of all other elements which were detected in the sample. So we compute directly concentrations instead of masses, which is much more accurate than measuring the masses. So here it comes. And in the background, it also opens the logbook where we have all the metadata available, and it will look for the numbers it needs. Oh, I interrupted the sorry for that. Import, yes. So now the two peak list files, the PKL and PKF, were merged together. You see with red which new entries appeared. And then you still have the possibility to intervene and change some entries before we proceed to the identification based on the library. But if I continue running, the program will enumerate all peaks and assign one element from the library. For all the 600 analytical lines we identified. Of course, some of these lines are background lines, where you see here this BKG, and they are also corrected or identified. And there is also a way to handle interferences. So one element can have an analytical line where another element has its own, other line. And if they are too close to each other, it is impossible to resolve them by fitting. So in this case, we apply a numerical subtraction of the contribution of the interference, and the leftover will be assigned to another element. So this calculation takes a bit of time, kind of a few minutes. It's calculating in the background, but screen updating is disabled in order to speed up the process. And now the calculation is ready. And the program identified the possible elements. In this table, you see the results sorted based on the Z, so the atomic number. And here you see the measured masses. You can set uncertainties. The background components together with the uncertainties by adjusting these columns. So if I set a background spectrum, then background mass values will be entered here for relevant background components like hydrogen, boron, nitrogen and oxygen come from the air within the sample chamber. Fluorine and maybe carbon can be originated from the Teflon foil that we use for wrapping, and aluminum, iron, and to some extent copper are construction materials of the facility. And the germanium is the material of the high purity germanium detector crystal. And also there is germanium in the bismuth germanate scintillator crystals. So these are always present in the background, and these can be corrected for. But now you see that for every element we have quite a few analytical lines. The only exception is a few exceptions are from this rule, like hydrogen and boron. They have only one line, and also probably lead. But most of the elements have quite a few lines, and they can be statistically verified if they are in accordance. And the program shows here a number, a quality factor, which is computed from the identified lines over all available lines in the library. And if this is close to 1, that means you found almost every significant key analytical line. And the mass value is also in line with the others. So that means it is well acceptable. And there is a high probability that the element is present in our sample. If we go down somewhere else, then we can say that this is just a false coincidence. Let me show you down here. So for each sample we have thulium or something like that, which is a strange combination of background lines which are disidentified. But here you see that the sample masses calculated from different lines are not in line, and this quality factor is very low, so we can safely reject this element. And if you have a consistent set of analytical lines like here, you can check or uncheck individual lines which you want or doesn't, if you don't want to be part of the statistical averaging. This number is the weighted average of all lines that you select. You can do selection and unselection with this star symbol. So if let's say I want to get rid of this line, then I remove this star, and the program will recompute. And this is the standard deviation from the average for the masses, and this is for the energies. If you see here outliers, like here, this is way too high, so then you can remove this line, and then this deviation disappeared, and this final value is recomputed. But if you check out, so this is 4.10. If I put this back, it will be 4.11. So only tiny changes are made by these outliers. And in most of the cases, the analysis is very reliable. And the other thing is, what you have to notice is that we have here a lot of lines which are of 6%, 8%, 7% statistical uncertainties. And by doing the weighted average, this can be reduced to a kind of 1.7 or 2%, depending on how you calculate. And this is a key step to make the analysis results precise, because this way the statistical precision of the analytical lines can be much improved. And wherever you see this blue highlight, those lines are fitting nicely to the tendency, so they give agreement masses like this. And wherever you see some higher mass, it's probably an improperly corrected interference. So those ones you can unselect if you wanted. And still this quality factor is rather high, so we can be very confident that silicon is present in our sample. And you know, just like in case of potassium, we have plenty of analytical lines with agreement masses. The same is true for calcium and for many other elements. So basically, the task of the analyst is to go through this entire table and check each element and see if the masses, what the program determined, is correct and it's in line with the weighted average. And then once these data are checked, then this table is automatically updated. So if I change here something like this value, then it will influence this table. So I can always decide that I don't believe that there is holmium in my sample. So if I just remove this element from the calculation, then the entire table is once again updated. The other trick is the oxygen. So oxygen is very poorly measurable in our case. It has a very low analytical sensitivity, and as this is an oxide, a geological material, we can safely assume that it is fully oxidized state, and we can compute the oxygen content of the sample based on the oxidation numbers and the stoichiometry. So we provide you with 4 columns as a result. So this is the atomic concentration, molar concentration. This is elemental weight concentration. And this is elemental weight per all oxides, like in X-ray spectrometry. And this is the oxide weight per all oxide compound. So in this case, it would be kind of aluminum oxide over all oxides of these elements. Because geologists sometimes specify these values rather than these ones. Here you can fine-tune some details like the thickness of the sample. You can put here some density, like let's say 2.5. And then we can make a so-called self-absorption correction. Although gamma rays and neutrons are highly penetrating particles, they still interact with the material of the sample already. So this matrix effect can be corrected for by correcting for this negative bias. and this is done by this step. Usually the main components are just marginally adjusted if they have both high energy and low energy lines. So these self-absorption correction affects elements like boron or rare earth elements, which are predominantly analyzed by their low energy lines, and they do not have any high energy analytical line. Okay, so that was all about concentrations, and now this correction is over, and now the results are recomputed for the self-absorption matrix correction. And I have here another version of this same table where I already did revision of these analytical lines, and I also copy pasted the certificate of this material. So this is a United States Geological Survey reference material codenamed Cody Shale SC'21, and these elements or oxides are listed in the certificate. And so this table is shown here. And as geologists, they usually put the composition of major oxides in this form. So for minor components and trace elements, you should check this column, while for major components, you should check this column. So here you see that, for instance, silicon oxide content is 63%. We measured 64%. Aluminum oxide is 13.7. We have 14 for iron. We measured this total iron content. We cannot differentiate between iron 2 and iron 3, but this would be 5.1, and we measured 5.3. Calcium oxide, it's 2.6, and here we have 2.4, but it has rather high uncertainty, so we are still within the uncertainty margin. We have magnesium oxide 2.7, we have 2.8. Sodium is 0.9, we have 1.04. Potassium 2.77, we have 2.9. So you see that our data are rather close to the certified values. Also for titanium, so here is 0.63, and we have 0.62, which is almost a straight hit. For boron, we always tend to say that our method is the best for boron analysis, and we always ask the service, the standard reference material providers to provide boron data or revise boron data, because boron is rarely specified and rarely analyzed by other methods. So in many times they do not have a certified value, but only recommended value. That means it wasn't measured by more than one method, or the results were not in line. So boron is always our key data. And you see that we are still in the uncertainty margin. Chlorine, we have 50 ppm certification, 51 ppm. and so on and so on. We have measured also samarium, gadolinium, which are not in this list, but we are still confident that these values are good. These are good indicator elements in the geochemistry, and that's why we like to analyze geomaterials, because neodymium, samarium, gadolinium, europium, so these rare earth elements are very informative for our geologist colleagues. And even more informative results can be generated if we do both the program activation analysis and the instrumental neutron activation analysis on the same sample, because then much better detection limits can be achieved and much broader selection of elements can be analyzed. Almost every relevant element can be studied by the combination of these two element analysis techniques. Okay, we are back here. I hope you can also return. And now I would like to continue. If you have any questions, you can always ask in this chat window, or please feel free to interrupt me. In the remaining part of my presentation, I would like to show you some practical examples where our technique can be used. And the first set of samples would be heritage science samples. So here you see that quite large pieces like helmets or face masks can be measured. We have here polished stone tools from prehistorical humans. These are also very delicate and possible to provenance. So provenance study means that you try to trace back the origin of an object based on its composition or some trace element composition pattern. And by measuring the composition of these prehistoric stone tools, you can have a clue about the movement of people's population and their trade relationships between each other. You can measure very well glass kind of matrices. Here we can nicely differentiate between old-fashioned glasses from medieval and more modern glasses based on the boron content, because boron was later added to the glass melt to make the glass shiny and nicely looking. But this invention was dated well, and all the glasses which were supposed to be produced before this cutoff date are of low boron content, and that makes easy to figure out falsifications or forgeries when the glass is not as it is stated. Similar provenance study can be done by trace element composition for lapis lazuli samples. Lapis lazuli was very widespreadly used blue paint in the Egyptian and medieval times, but only 5-6 mines are known where these are coming from, and fortunately they have different trace element patterns, so they can be nicely allocated to the mines. And this makes also possible to reveal the trading relationships between different people. The next example is a set of Inca ceramics. There was one exercise where we had the challenge to differentiate between ceramics made on an island and another set which was made on the mainland of Colombia. And if we check the composition of the ceramics and correlate it with the local raw materials available like soil, we can identify differences, and based on this we could say that a certain fraction of the potteries were made on the island and the other on the mainland. And of course there was a set where it was not clear and it was not easy to distinguish. So some more samples. Please note that for these excessively large samples, we can dismount the sample chamber, so we can accommodate even very large and very bulky samples. And this is also a quite large one, weighing about 5 kilograms. These are bronze objects here. This is a sword, which can be scanned from up and down. And say the welding, for instance. Now, this was a very nice example where we collaborated with Tilo Reren from England. And this was a iron object recovered from the Egyptian pharaoh's necklace, and it was fully corroded, so from outside it was not possible to see anything. And with radiography we could reveal that it was not drilled through, but first it was hammered to a flat layer, and then it was rolled to form this cylinder. And the composition was also quite exciting, because relatively high nickel and cobalt and germanium content were identified by PGAA and also PIXI, and that was the evidence of an extraterrestrial origin of the raw materials. So we assume that this piece was fabricated from a meteorite fallen down to the earth, and that's why it has some cultic and sacral significance. In geochemistry, bulk analytical capability is very useful, because we can measure those either powdered samples or whole rock samples without any sample preparation and digestion, and without the risk of any sample contamination. And as it is non-destructive, the sample can be measured with other techniques in a subsequent measurement, and all the required and relevant elements can be measured. There was one interesting study by a colleague, when she was interested in the subduction of the tectonic plates, and it was revealed that the boron content of these metamorphic rocks is a good indicator of the volcanism and the subduction mechanisms under the sea, for instance. So if there is a middle sea valley like in Iceland, where there is a recent volcanic activity, if you go further away from this volcanic area, then the boron content changes accordingly. So the boron element, and also in correspondence with chlorine content, these two elements are good indicators of the volcanism. And as I mentioned, there is a good complementarity between prompt gamma activation analysis and instrumental neutron activation analysis, So here you see a plot where with black dots you see the outcome of PGAA analysis, while with red you see the results of instrumental neutron activation analysis on a Japanese basalt reference material. And this yellow highlight shows the confidence band. And you see that in certain cases there is an overlap in element analysis capability, but instrumental neutron activation analysis can measure much more trace elements than PGA can do. While there are elements like silicon or boron or hydrogen, which can only be measured by prompt gamma activation analysis. And this is a certificate study very similar to what we use for demonstration today. This was the lapis lazuli, which I showed you already, and we have a long-standing collaboration with the National Museum of Hungary for the provenance analysis of chipstones tools. So this is also from old mankind. And now we have a broad database of chipstone tools, which includes not only Hungary, but all neighboring countries, and also Italy, some part of the Balkans, and up to Poland. And based on this database, now we can classify one unknown sample to the proper origin of the raw material, and that can help understanding and the classification of the museum goods. So here you see some table where so this Lipari is an Italian area. There is island of Sardinia, island of Milos from Greece, and these groups can be clearly separated. And these other ones are from the Carpathian Basin, so from Hungary, Romania, Slovakia, and some parts of Poland. And very interesting revelations could be achieved. So if you have a hill which cuts different populations, and if you find some pieces of this stone at the other side of the hill, then you can say that there was definitely a trade between the two population groups. So this is the the glass business I was already mentioning. There is a clear trend between different manufacturing workshops. So these many workshops had their own recipes to prepare the glass, and even major component composition like calcium, sodium, or potassium were different significantly enough to create groups and differentiate between different manufacturers. In the following slides, I would like to show some examples for the position-sensitive element analysis, which we call PGAI, prompt gamma activation imaging. And in this plot, you can see the relation of our technique relative to other well-known element analysis technique in material science. So this domain would be nanotechnology, this is microscale, and this is bulk. And you have very nice and very sophisticated methods to measure tiny bit of details of the materials, but those methods have very little sampling volume. So if you are interested in the bulk composition, the representativity of these techniques are not always enough. And on the other thing, the penetration depths, so the sampling depth of those methods are also not always satisfying for the representative measurements. And in these cases, PGAI and PGAA can help, where the resolution is not so nice, but the result what we generate is very representative. This is again the sketch of the NIPS normal station, and there are practically two ways to generate spatially resolved data. One is what we most typically use is this so-called isovolume approach, where we have a pencil beam of neutrons and a highly collimated gamma detection angle, and that defines the intersection of these two as the isovolume, and that's the source of the analytical information. But still, this is not very efficient method because you get rid most of the neutrons and most of the gamma rays. So the spatial resolution comes with the price of lower measurement productivity. And there is the other principle, which is called tomographic principle, what we use for neutron tomography. And with adequate modification, one can also use the same mathematics for emission tomography. So you measure the emitted gamma rays of the sample with some spatial resolution somehow. And then you apply a mathematical reconstruction procedure to reach the three-dimensional distribution of the emission. Here we have technical limitations because the detectors that we use for gamma detection are not enough spatial resolution to realize this emission tomography principle. But the technology is improving. There are already development phase detectors which will have let's say 1 millimeter pixel resolution, and this will open the way for the future to apply this more productive measurement technology for generating really three-dimensional data. But until we reach that point, we use this isovolume approach. And if the object is rather large or has a complex shape, we need to account for the self-absorption and self-shielding of neutrons and gamma rays. And this can be facilitated by a technology called Monte Carlo calculation, where with computer simulation, we follow the propagation of radiation within the sample and within the sample geometry, detector geometry. And this is working on generating a large number of random numbers by computer. And it has model functions to describe the individual events of neutrons and photons and electrons. And they are parameterized, so you need huge numerical databases to feed these algorithms. And once we set up the sample geometry and the detector geometry is already ready, then we can start such simulation, and we can have a neutron profile, intensity profile like this. So at the beginning of the front side of the sample, you have higher neutron intensity, while as you go deeper and deeper, the neutron intensity will be less. And then, of course, gamma rays emitted from the backside of the sample has to travel through a longer path length towards the detector than this one, so they will be differently attenuated. and this can be quantitatively corrected for using these Monte Carlo techniques. The real merit of PGAA NT technique, so the combination of imaging is with element analysis, is that we can better explain our results based on the joint interpretation of these two data sets. So alone element analysis and alone imaging would not be so informative than if the merger of the two data sets. So this is illustrated in an example of a stepper motor. This is a very old one. Here you see the radiogram, and we measured gamma spectra along its long axis, so slice by slice, and then you get such peak patterns. This greenish one is the iron, then the dark blue is copper, and here you have hydrogen, no, boron and hydrogen. And without knowing the internal layout of the object, it's very hard to explain. But if you look inside, then you can identify that copper comes from the copper coils, iron is from the iron rotator, like here, and then hydrogen and boron comes from the printed circuit board, which is at the bottom of the the stepper motor, which is over here. So by the joint interpretation of imaging information and elemental composition measurement, we can better characterize such a non-homogeneous object. Here we can also highlight some inclusions in geological materials. So sometimes we have local enrichment of certain components, and the wanted component is not distributed evenly all over the sample. We can also make dynamic processes. There was one experiment where we analyzed historical building materials from Venice, Italy. And the conservators were afraid of the effect of the seawater on the old buildings. So we created an artificial sodium chloride solution and let it absorb by the stones. And then you see that different limestone or marble samples picked up different amounts of this sodium chloride solution, and this is an indication of the pore volume inside these stones. Of course, Carrara marble was found the best one, which took up little or only marginal water. And then we can also do this dynamically. So if you select a plane somewhere, and then you put water below, and then you start looking at the data when the water front would reach this area, and then you can even check the ions, if the mobility of sodium and chlorine would be equal to hydrogen or different. And in material science and in many aspects, PGA alone is not a holy grail method. So we often collaborate with colleagues from other measurement techniques and other science disciplines, and then we can execute complementary and interdisciplinary studies. So one of these was a numismatic study with collaborations from the University of Turin, And here we used to see the silver content of these coins, which are visually assigned to different emperors of the Roman Empire or to local tribes which lived in the neighborhood. Um, so the real commercial value of the coin was proportional to the silver content, uh, and it was very interesting to see that if you plot the silver content over time, then you see a decrease. So that was the proof of ancient inflation. So subsequent emperors or tribes um, tendenciously diluted the silver coins with copper and then made it, let's say, cheaper in value. And that was the first evidence of the ancient inflation. We can also have hint from imaging about the positions where we need to study. This was a large shield, about 60, 70 centimeter large. And of course, it is unproductive to scan it through entirely by program activation analysis. So we first made radiograms by X-rays and neutrons. And if you compare the two images, then you could see already spots which are more contrastful in the X-ray image than in the neutron image, or vice versa. And this can already give you some indication what elements can be present at that area. So this is a rivet. These are some organic residues, some heavy metals like lead. And then by knowing this information, we can focus our element analysis efforts more effectively on the interesting part of the object without needing to scan through the entire thing.